Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Welcome to the last session for today, and it's my pleasure to introduce Yogesh Simmhan. He is currently a postdoc here at IBM Research. We did decide to allow one IBM, it's tiring.
I just switched companies.
He's a postdoc here at Microsoft Research. I don't know where I got that IBM Research post. Anyway, he is. We decided to let one Microsoft person into this thing, and I'm really glad it's Yogesh. So Yogesh, go ahead.
Thanks, Dennis. All right, I'm in the eScience group at MSR, and we essentially work on trying to see how we can leverage existing and emerging distributed technologies to better enable scientific applications to run. Many of the researchers in our group are computational biologists, so genomics applications are a common suite of applications that we try and experiment with new platforms. And I'll be talking about some of our experiences with migrating a couple of our genomics applications to the Azure cloud, and also some of the middleware that we ended up building during the process to enable this to happen much easier. And there's, of course, a collaborative effort with other groups, both within Microsoft Research and also with some help from Girish, who interned with me last summer and helped make this happen. We've heard since the morning about the challenges that scientific researchers are facing with the data deluge in eScience. And this is driven a lot by the pervasive deployment of sensors that might measure something like the ocean characteristics. You might have shared instruments like next-gen sequencers that produce terabytes of data as they sequence human genomes. Or these can be from simulations that you run, let's say, to do weather forecasting. And scientists are increasingly being challenged by the resources they have access to in order to do the various data processing from this data deluge. And there is often a non-uniform distribution of the workloads that scientists have. So if they conduct a field campaign or an expedition, they might suddenly need a lot of resources, and later on during the year, they might not need much of it. Or if you got a paper deadline, like was illustrated earlier today, paper deadlines usually have a lot of computation involved with them, and then you go back and do your normal stuff. So this non-uniform computation produces certain variable workloads, and also the fact that there's a lot of collaboration going on in eScience disciplines. So you need to share both data and analysis with collaborators who might be spread about globally. And if you think about, let's say, the global population of researchers, which I've sort of listed on the x-axis, and on the y-axis you got the resources that they need in order to do their science, you'll see something like a power law distribution, where most of the researchers are content to run on workstations with things like scripts or Excel, which seems to be pretty popular. And there's a small fraction which make use of high-end computation like HPC systems. But as scientists start dealing with more and more data, this whole graph is shifting to the right, and they actually need to migrate from, let's say, a workstation where their problem won't fit. And they have to start thinking about, let's say, migrating to a local cluster. And especially for scientists who are in the tail end of this computing spectrum, jumping from a workstation environment to managing and maintaining a local cluster is a whole different world. And the cloud computing pattern that we've been talking about since the morning makes it easier for researchers, particularly at the low end of the spectrum, to get access to resources on demand. So the whole idea is that you're democratizing access to the resources through cloud computing. And there are several advantages to cloud computing, as we all very well know, such as on-demand availability of resources. You can scale from 1 to hundreds of nodes and scale back to 1 once you're done using them. There's also the ease of management, so you have virtual machines or you have higher levels of abstraction, so you don't need to be worrying about the low-level hardware. And you also get economies of scale in that it's cheaper to use than maintaining your own cluster. And you get pretty simple, reasonably simple interfaces for accessing these through REST web services. And you don't have to go through complex programming tools. Some of the common classifications of cloud architectures depend on the level of abstraction that you get to the various cloud resources. So infrastructure as a service, such as exemplified by things like Amazon EC2, virtualize the hardware, both the compute and the data, and give you access to a VM that you have complete control over. And at the other end of the spectrum, you might have applications that are virtualized, such as mail systems or things like Salesforce. And you can configure the application, and that's pretty much all you can do. And you're guaranteed that it'll scale out, but have no idea what's underneath the covers. And Windows Azure sort of sits somewhere in the middle, so it gives you a .NET runtime as the platform, but also creeps a bit into the infrastructure space by giving you access to a user mode Windows virtual machine. So much of today's the talk right now will focus on somewhere on the infrastructure and platform space, and in particular Windows Azure as the cloud computing example. So cloud holds a lot of promise for e-science, but it doesn't come without its penalties. And as Paul Watson observed earlier on today, it's pretty complex to take an application and push it into the cloud. It's non-trivial, and particularly when you're talking about scientists at the tail end of the spectrum, these are not experts. They cannot spend days or hire a programmer just to take existing applications and migrate them to the cloud. So we need to make it easy for scientists to migrate existing desktop applications that they might have running and push it into the cloud. And there are three main challenges to this posed by the current cloud model. So one is how to get your application deployed into the cloud, and that essentially means right now you have to actually manage virtual machines, install your OS, install your software, all the dependencies, and upload it into the cloud and get instances running. And anytime there's a change in your code, you have to go around and do all these steps all over again. Application execution also changes, because typically if they're running their own workstation, it's a local execution. They might be invoking a local method, or they might be running a local command line application. But once the application moves to the cloud and your client is in your desktop, they have to deal with remote execution using the cloud data structures like queues and so on. So passing parameters, and particularly passing data, it becomes a challenge, because many of the scientific applications, as we've seen, use file as a first-class parameter. And the fact that you really don't have a global file system, a shared network file system as such, when you're talking between the desktop and the cloud, means that you have to essentially have out-of-band mechanisms of pushing files between the desktop and the cloud through shared cloud storage. So all of these present challenges to scientists who want to migrate their applications to the cloud. Just to give a quick description of Azure, just so you know what I'm going to be talking about. Azure has worker roles, which are essentially encapsulate, these are virtual machines which encapsulate a particular application logic. So each type of worker role has a particular application logic. You can think of it as a science application. And you can create as many instances of your worker role as you want, and each instance is going to be running in its own VM. You can't directly access a worker role instance from the public internet. So you have to go through the cloud storage abstractions that are provided. And these are essentially queues, reliable queues, queue data structures, for which you can use, for example, to put a job request and get a response back. You also have simple tables, which are like name-value pairs, where you can run simple queries. And you have blob storage, which is used for storing files and collections of files. And if you think of a typical science application that's running in your desktop, let's say it's a command line application that you're running, or it might be a .NET method that you want to be invoking. So you got the user application in your desktop, and you have a set of application dependencies, which might be other libraries that the application refers to. That's also present in the desktop. Your current user client might just be a shell, a command shell from which you just execute that application, or it might be a main method that you call a .NET method, call the other .NET method from. And this is what scientists would use on the desktop. But the moment you start thinking about migrating it to the cloud, you first have to think about marshalling and unmarshalling parameters that you pass, because it's going to switch to a remote execution model. You also need to start thinking about pushing files between your local desktop and the cloud through cloud file storage. You then have to start packaging messages and putting it on cloud queues so that you transfer requests and response in an asynchronous manner between client and the cloud application. And finally, you need to package this all up into a VM or a worker role and upload it to the cloud so you can create instances of that and start running it. So everything except the yellow boxes over there are additional code you have to write in order to get your application running in the cloud. And this, for many users, it is non-trivial and takes a fair bit of time. And it's a big trade-off for them, whether to even try it or not. So the goal of the work we did was to see if we can improve the accessibility to cloud by making it easier to deploy applications from desktop to the cloud, invoke applications, either from command line clients or from workflows, and make sure that we handle file movement and transfer across desktop and the cloud transparently. And the whole idea is to do this with minimal user overhead or code change. So what we proposed was the generic worker framework for Azure, which is essentially a common worker role or a VM image, if you want to think of it that way, that's capable of dynamically deploying and executing applications that are registered with it, and being able to invoke these registered applications on demand from desktop clients, workflows, or just through plain APIs that we provide. So there are essentially 3 steps to the whole thing. So the first thing is to actually get your application registered so that the framework is aware of your application so that it can run it on demand. And the key to this is to keep things simple. We expect these applications to be, let's say, .NET methods that you want to invoke, or these could be command line executables. And we can definitely, the same analogy applies to Java programs also, though we haven't, we have a proof of concept, though we don't have it working as part of the framework yet. So the idea is that these are self-contained applications, and all the applications and all their dependencies, for example, are packaged up into a bin directory where it's available. And we provide a simple command line tool called register, to which you can pass the location of your application binaries and its dependencies, and point to a startup point inside the application. If it's command line, you just run it as is. And you also give the signature that the command line expects. If it's a .NET method, you just say which .NET method in the library that you have in the bin directory you want to invoke. And we essentially figure out what the input and output for that method is through reflection. So to give an example, so if you had, let's say, a class that you have on the desktop and called mathOps, and let's say it's got 2 methods, add and multiply. In order to get this registered with the generic worker framework, you would type something like, you'd say register, and you'd say it's a .NET application, and you give it your own logical name to it. Let's call it my mathop. And you point it to the class, and this is the class name for this is sample cloud app.mathops, that has the application and the directory where the particular application resides. So this would contain the DLL that has this particular class and all its dependencies. If I were registering a command line application, let's say a BLAST application that's commonly used in genomics, I would do something like this, where I actually pointed to the actual command that I would be executing within the cloud, and pass parameters as almost like templates over here with some description on what the parameter types are. And again, it would point to a directory where the binary and all its dependencies are present. So behind the scenes, when you actually run this register, what happens is on the client side, it essentially takes the entire bin directory that you point to it and ships it off into cloud storage, into a particular container. and also registers a couple of entries in tables that's maintained in the cloud on what application it is and all the parameters that it expects. So at this point, your application is registered in the generic worker framework and ready to run. So nothing is running yet. It's all present in the storage, but it's ready to be run right here. So in order to run the application, there are a couple of ways you can do that. So the easiest way is to actually use another command line application. So command line applications are pretty much the lowest common denominator almost, because that's simple for scientists to relate to. You just go open up a shell, type a command, and you have your application running. So the idea is that you can pass all the input parameters that either the method or the application command line expects just as command line parameters to the invoke method. And internally, what this does is it actually uses APIs that we provide to marshal these parameters as an XML message. This gets put in the queue and ready for execution inside the cloud. And we'll presently see how the entire process takes place. And once the execution completes, it gets a response message back as an XML message, gets unmarshaled into .NET objects, or if it's invoked from the command line, into just things that are printed on the screen. And if you were actually running it, this is how it would look. So the earlier math, the class that you registered, you just invoke it like this: invoke mathops add, and pass it to the int parameters that it expects. And this is what you would see. And in between these two steps, it would have actually run the application in the cloud and fetched the response back. And all of that happens asynchronously in the background, but as far as the user is concerned, it seems to be synchronous. You could do the same thing using the API that we provide. So you just create an invoker, passing it the name of the application. And what you're doing over here is just calling the mathops.add method using this very intuitive signature. This is how you do it if you're doing it locally, but if you're doing it through the invoker API, it looks pretty similar. So the overhead for the user is much lesser in order to use that. Behind the scenes, a lot is going on. So initially, the application inputs are pushed off into blob store. So if it were files, the files would be pushed into blob store. And the marshaled input parameters are put in a queue that various workers are listening to. So the workers that you have running in Azure, they're all the same generic worker. Irrespective of how many other applications you might have, all you need is to install and maintain a single image running in the cloud. And as your job goes to the top of the queue, it gets picked up with the next available worker that essentially looks up the table where the signature for the application is present and downloads the various binaries required for that application into local storage over here, and also downloads the input parameters. Let's say if there are files, they would also be downloaded to the local virtual machine drive. And then it actually does the execution of that application locally. And the same happens for the output parameters. They would be, if there are files, they would be pushed back to blob store. The response would go back into the response queue. And the client over here would be polling. The library we have would be polling for the response. And once it comes back, it would print it to screen or return it as .NET objects. And if there are file parameters that are generated, they would automatically be downloaded if you had asked it to. Lastly, we also take care of automatic data transfer. The key idea is that users should not have to worry about the various steps of data transfer that takes place. For example, between your local desktop to blob store to the virtual machine drive and on the way back for the output parameters. So all of this is done automatically for you because the file parameters, let's say in a .NET method signature, is recognized and files are handled specially. It doesn't go through the queues, but only references are passed through the queues, but the actual file itself is staged into cloud storage and automatically downloaded at both ends. And we also provide some various caching mechanisms to actually make the whole thing more efficient. There are a couple of genomics applications that we've tried out. One of them is the genome phasing application, and the whole thing is structured as a scientific workflow, which is implemented using the Trident workflow engine that we have. So the key idea over here is that you could have a workflow that contains of various activities. And each activity could typically runs on a local desktop. But you could essentially replace, let's say, the most compute-intensive activity as a cloud app activity that actually runs things inside the cloud using the generic worker. So as far as the user is concerned, they just pop out the single activity that has the compute-intensive task with their own, with the cloud app activity. And the whole workflow runs locally, but only things that need to be run in the cloud are pushed off to the generic worker. And the other application that we've tried out is a slightly more long-running compute-intensive activity called genome-wide association study. And that typically runs on several hundred HPC cores for almost a day. And over here, what we essentially did was, the whole thing over here was one big .NET application. And what we essentially did was take the portion of the code that launches these the two MapReduce tasks onto an HPC batch queue and replace that with calls to the invoke method in the generic worker. And the whole thing essentially scaled out transparently onto the cloud, and you get the response back. And the application itself has very minimal code change. And from the performance measurements that we have, the initial measurements we have, we see an overhead of less than 5% introduced by our framework, and almost 95% of the entire time is spent in actually running GWAS application. And we also see linear scale up as we increase the number of workers to get the entire job done. Again, we haven't scaled it up to the hundreds of cores that the full-fledged GWAS application requires, but from what we have seen, it seems to be scaling up linearly, and we currently have experiments going on to see if it works for much larger cores also. So there's a bunch of improvements possible, meaning going beyond .NET and binary executables to Java and MATLAB, which are pretty common in the scientific space. And also try out things like dynamic scale out of worker instances based on the demand that you have in the job queue. We have all the pieces in place in order to do that. The question is we just need to sit down and actually get it done. And finally, there are also lots of opportunities for cross-scheduling across multiple resource platforms. We've shown that a little bit with the scientific workflow, where you run some of the activities on the desktop and some inside the cloud. But getting this done automatically, so you could potentially run part of the workflow in an HPC cluster, something else in the cloud, and something else in the desktop, and have the scheduler figure out automatically which pieces need to be run where based on various metrics, is something we are currently looking into. So as I've tried to show, cloud has a bunch of opportunities for e-science, but accessibility is still a problem. And the generic worker that we propose has reduced the user and coding overhead for some of the genomics applications we have tried out with minimal performance penalty, and it's pretty intuitive for users to use. So thank you, and I'll take questions.
Specific question regarding the library dependency. So when you use this framework to resolve the library dependency, can you maintain the hierarchy? If I have a hierarchical, like for example, in different folders, right? Can you preserve that structure when you know that?
Right. So right now, it's pretty simple in that if you got the bin directory and you got a bunch of subdirectories in the bin directory, that will be preserved. And the trick to doing that is essentially we zip the whole directory up into a single blob and push it off into the cloud rather than pushing off individual files. And at the other end, we just uncompress the entire subdirectory, and that's what the application sees inside the virtual machine.
Just a pretty specific question about the last application that you mentioned. So you had kind of a MapReduce-like job that was running in an HPC cluster. And was that really MapReduce running or something like?
No, it wasn't MapReduce. It was a MapReduce pattern. I'm sorry. I should have been more. Yeah.
And then you ported that to the kind of .NET and to Azure. But that was.
It was already a .NET application that had a MapReduce pattern. It essentially split a file into multiple chunks, and each of these was run on a different core in an HPC cluster. And the results were collected back by yet another task in HPC.
And that application you moved on to Azure.
Yes.
And did you have any? So this is not a question. How was the performance then, kind of comparison?
Right. There were some. So as you see, the raw penalty that we see is about 5% in running this in the cloud. And this time you see over here is the time it would take to run it on a local machine, not on HPC. So the penalty for HPC is quite likely less than the 5% you see over here. One of the advantages over there is that you have a shared file system in the HPC cluster, while here you actually have to push things into the cloud storage and all that. We haven't actually done measurements of comparing HPC against cloud. That's currently under progress. And we just need to make sure that we can go to 100 VMs over here before we can do that. That's all. Yeah.
For something like this, what is your feel that how long a compute job do you need to have for it to become worthwhile for you to offload it out there? At what point, and I assume that part of that 5% is fixed cost.
Yes.
And some of it is dynamic, but
Yeah.
some of it is fixed, right? So
We've seen, this definitely is not going to work for applications that have a turnaround time of, let's say, just a minute or so. Over here, if you see the total, these are in seconds, so the total penalty you see over here, and all of this is without any optimizations in place, is close to probably 40 seconds or so. So that's the overhead introduced by the framework. And something like this, which is downloading the application binary, is going to be a function of your application size. So that's not a fixed cost. It's going to change per application. But things like the queue wait time and so on, these are endemic to the cloud, the fact that you're running on cloud data structures. So I would go and say something like, if your application takes more than 5 minutes or so, it might be worthwhile given that the coding penalty is much lesser over here. But if you've got a great grad student who's got nothing to do and actually code it up specifically for the cloud, you can definitely get a marginally better, more efficient implementation on the cloud rather than using the generic framework.
So I would think the location of the data would be if you have an application that has a lot of data locally, the cost of moving that is going to be quite high. But then if you have an application, we have a large data collection in the cloud already, and your application, when running it locally, knows how to access that data, then it should be much better.
Right, and in a sense that at that point it becomes a trade-off between does your shared file system in your local cluster perform much better than, let's say, access to blob storage from within the cloud. And sometimes, more often, it's probably, the answer is probably no. Like gigabit LAN is going to outstrip cloud, at least from what it seems right now. So for big data, it's probably not yet prime time, I would say. But,
So is that blob, is that part uploaded to the worker for every single worker and every single time that worker is run?
So every single time the worker is run. So we have some optimizations on actually data movement between desktop and the cloud. So if you're running the same worker again and passing the same, or some of the parameters are still the same, the file parameters, it is actually intelligent enough to just pass references and reuse copies of the data that's already there in the cloud. So yeah, but if every parameter that you pass is unique for every invocation, it is going to be transferred into the cloud each time.
What about the code? Because you mentioned in that blob was also code.
Right, the code is transferred only once at the time you register. But when you run it, every parameter that you pass is pushed into the queues or into the blob store.
All right, thanks again, Yogesh.
Thank you.
Okay, our next speaker, who I will let him set up while I'm introducing him, is Chia-Chi Teng from Brigham Young University, and he's going to talk about implementing a DICOM image archival solution on Azure.
My name is Chia-Chi Teng. I'm from Brigham Young in Provo, Utah. Like most of us here, we're trying to figure out how to incorporate cloud computing into our curriculum. And one thing that we try to do is to encourage students doing this as part of their senior capstone project. And a few students that approached me and they decided this is what they want to do. Part of their capstone project, they have to come up with a business plan, and then they have to implement it. So the rationale of their implementation for this particular project is this. medical imaging and the volume and the procedures is increasing dramatically in the U.S. And other parts of the world as well. As you can tell here in 2010, right now, we're getting close to where are we here? We're close to 1 billion procedure done per year. And this is just U.S. alone, as you can see the 2014 forecast. And that's the number of procedure. If we translate into the number of bytes, and this is only the primary copy. We're not talking about the replication and then the backup and so forth. The primary copy, we're already talking about 50 petabytes today, and it could double in 4 years. If you talk about HIPAA, they require hospital to preserve data at least 7 years. So if you accumulate the past 7 years data, we're talking about hundreds of petabytes of data in the U.S. alone, and somebody have to store them. And in the typical hospital environment, they implement what they call a PACS system. And they would have different workstations and servers that perform different roles. The radiology workstation that will acquire image in different modalities, CT or MRI or even ultrasound, and they will be pushed into what they call a DICOM server that implements the standard DICOM protocol, and from there it could be distributed to different type of workstations. And usually they also have an archive server that files that are not used frequently would be pushed back to archive. And this is usually all inside the firewall for security and privacy concerns. But the consideration is that the cost is increasing dramatically, and not just the cost of purchasing the machine, but also the management, maintenance, and also the utility. And hospital usually runs in downtowns where the utilities are not the cheapest, of all places. And then the backup solution, they're usually required to have what they call a third copy. In addition to replication in-house, they usually have optical or tape drives that have the third copy and then store it elsewhere in case there's a disaster and they track all the machines are gone, then they have to somehow recover from all the data that they have. And the current solution for most hospital, the optical or tape are really not efficient. If there's really a disaster happen, it's going to take a long time for the data to be recovered. And then, and the availability of those tapes and opticals obviously are slow, and the scalability for the tape and optical system are not so good either. The solution that the student proposed for this particular project is this. They would implement an archive solution in the cloud that the hospital can push those archive data that are not used day to day through the cloud, past the firewall, through the internet, and go to some storage in the Azure, the cloud platform. And then if there's really a disaster happen, they can really just pull those data back in a matter of hours and have things running again. But there are additional practical concern that gets involved once things go outside the firewall. Security is one. The industry has some standards that trying to solve this problem. They would have what they call a DICOM Part 15 standard that would encrypt the files, and you can also do SSH that secure the transmission between the two endpoints, and so forth. There's solutions that are being proposed to hopefully ease hospitals' concern for security, but more than that, the last two are kind of related: the liability and also the regulation. If the data in the cloud get lost or data get corrupted in the cloud, who's liable? I love what Dave Patterson talked about, that there's no guarantees, right? I mean, it's okay for my Facebook app games that data got lost, but it's a different story if the patient's data get corrupted or lost in the cloud. And there's really no regulation in that, for that matter, right now. The cloud is somewhat kind of regulated by the rules of telecommunication. But in another sense, they're used like utilities, right? If a telephone call gets dropped or if power gets interrupted, can hospitals sue those utility companies? And what happens here in the cloud, and there's a bunch of research and proposal that are being considered in those area, but this is just some practical concern that people usually run into, but that's not part of what they're trying to do. So, IBM is kind of the forefront of this kind of application of storage in the cloud. They are pushing big time, for this kind of application and solution for hospitals. Of course, they have their agenda, they have their whole infrastructure for doing this. And one interesting solution that they provided, they work with this company called Inside One. They provide basically the archive solution in the cloud. And of course, this is kind of a market that have a targeted audience. Mid-sized hospital who don't have a big IT staff, right? And they want to archive their solution, their data, and this would be an ideal solution for that. For people like Johns Hopkins, they have hundreds of IT staff. This may not be as important, but for a big segment in the market, that mid-sized medical health providers that they don't have an IT staff, this is the perfect solution that for the market. Well, Amazon is also working with Harvard in this kind of solution, a cloud-based medical imaging storage and management solution. So we know that there's value in these kind of applications, so that's what they decided to do. The medical image is usually in the format was what they call DICOM. DICOM is more than just a file format, but also a communication protocol. The workstations and the server in the PAC system, they all communicate through this standard protocol through TCP, and that's the DICOM defines that protocol of communication. Query, search, push, pull. Okay, it's all very well defined. So this is what ended up being implemented. So there are three type of instances or three components in the system. There's a DICOM server, which is a UI-less service that would communicate to the client through external TCP endpoints, and then they receive those DICOM requests for query, push, and retrieve, and so forth. And then there's when they receive a file, they would push it into the blob and send a message to what we call a DICOM indexer. And the indexer would parse the DICOM header and manage all those metadata and store those metadata and index them in a SQL Azure database. And there's a third type of instances, it's a web UI. For people who are not on the DICOM workstation, they can go through a web UI to either upload a set of images or browse for images that are in the archive. And they also implemented a thin abstraction layer, the storage APIs and queue APIs and the database API. This is so that in the future they can port this service to other cloud vendor or even on an IIS server for a small scale environment. And there's no reason why this can't run on an IIS server or even other type of cloud engine. But through this thin abstraction layer, they talk to the Windows Azure and storage and queue API and also the SQL Azure APIs. And it's really simple if for people who are familiar with .NET. They use ADO.NET and TCP endpoints is really easy to implement. That's one good thing about the Windows Azure. For people who are familiar with the .NET platform, it's really not that difficult to access those services. Okay, so the DICOM server is a worker row, and which is actually designed to have a UI-less service. So this instance, multiple instances of this could be spun up, and they would take DICOM request, and then they would push the work into the queue. And the DICOM index server will wake up, get the message from the queue, and then do the actual parsing and indexing, and be done with it. And Web UI is implemented in the web role, which is different type of VM that's has IIS included in it. It's optimized for the web type of UIs. And the great thing about this is you can implement things in ASP.NET and even Silverlight, which is something really cool that the student learn it, they love it. It's a very exciting thing in technology. So questions that they always ask is, what do I have to write code differently so that it will scale? Right? They're not used to writing things that runs on multiple instances of machines. So by doing this, they learn these simple principles. Right? The first one is they have to learn to program asynchronously. They learn this in operating system and some classes of threading, but this is slightly different, right? You communicate through the message queue and also use the storage blob APIs. You put some data in the storage and you pass some message in the message queue, and the other end they pick it up. It's all asynchronous, and more importantly, everything is stateless. Every time you do a process, you're not supposed to keep a state in your instance, right? This is something that they have to get used to and realize. All this programming, every instance is stateless. When you push a data into the blob and into the queue, you never know which instances of worker row in an indexer will pick it up. So this is another thing that they have to learn, kind of a stateless data flow architecture. Data just flow. You get the data, process it, and put it back. There's no state in any of those instances that you run. And every message go through the queue, and you go through the queue to pick up the message and be done with it. And the Azure message queue provide a nice feature is that when a worker wrote in the back end pick up a message, okay, that message is not really deleted. Right? The message queue give you a receipt, okay, and after you process that message and you say, okay, I'm done with it, then I take this receipt and I delete that message in the queue. For some reason, if my instances of worker row, the indexer, fail or died or something happened, I never finished, right? That message never gets deleted, and after a period of timeout, that message will surface again, and data is not lost, and that message get picked up by another instance of worker row in the back, and it will be done. So it has a kind of a built-in transactionality in the queue management. So it's kind of nice. So they learn not only to design it, but also kind of think in writing code that would scale. So why Windows Azure? And here are some of the answers that they gave me. They like C#, they like ASP.NET and ADO.NET and Silverlight. Okay, for people who are familiar with all these languages, Azure is a wonderful environment to program in. And Visual Studio, if you're familiar with C# and ASP, and you're familiar with Visual Studio, it's really, the switch is very simple. And a rich set of .NET APIs, like the TCP endpoints and all those APIs, which you would normally use as you write standalone .NET application, and they're all available in the Azure platform. And a rich set of third-party tools that are available online. Other people developed for the Windows Azure platform that you can download. One of them that they love is the Storage Explorer. You run the Storage Explorer, you can connect to different type of storage in the cloud, and you can browse through all the blobs and all the queues, and it's very a handy management tool. And another thing that they love is the local cloud simulation environment and the local fabric and local storage. Just kind of a side note, I was at 6CSE last month, and one of the keynote speakers, Carl Weidman, the Nobel physicist, and he said one observation he made is that the computer science student nowadays lack skilled debugging skills. And I kind of feel the same way. And for them, this IDE, and when they can develop and debug on the local environment, they can really learn how to debug their applications where some cloud platforms, don't have that luxury of running and debugging your code in the local environment. And simple deployment management interface on the web. Of course, other cloud platform has that as well. It's really not. That's why it's lower on the list. They also have some complaints about Azure as well. If you are packing third-party DLLs, sometimes you have to be really careful, kind of like the library issue as well. And Azure is implemented in 64-bit natively, and if you develop your application as 32-bit, sometimes there's little glitches that that may get you. Cloud debugging. I think most of the cloud platforms still kind of lack this. Just in case your program runs fine in a local simulation, but there's problem running in the cloud. Of course, it always happens. It's really difficult to debug your code in the cloud, right? So, but the only thing that most cloud platforms supplied is kind of a logging mechanism. That's what they do. So, let me move along. So also that something that they learn is the development cycle of a cloud environment. You create manage your services in the portal, and you set up your dev environment, and then you develop and run and debug your project in the local fabric. And then you deploy your project in the cloud after it runs fine in the local fabric. So let me just kind of give you a quick demo of what they have that demonstrate that development cycle. So, okay. So Windows Azure portal is this for those of you who haven't seen it. You can go there and create services, create storage, and so forth. And then from here, you can also manage all your services. And once your service and storage is created, you'll be given some keys that you use to access your storage in the cloud. And then in the Visual Studio, typically, they did this in a semester about 10 weeks worth of work. With 4 of them probably wrote about over 2,000 lines of C# code. But you'll see a project and then different instances of the component. So here we'd have an indexer instance that's in the worker role, a server instance that's also in the worker role, and Silver Surfer, that's the web UI in Silverlight, that's in the web role. And then in the project here, okay, you'll define these roles, okay, and you can also come here and manage it. So for example, here I say I only want one instance of this in the worker role. And if I run this on the local fabric, okay, instead of instantiating virtual machines like you would in the cloud, here I actually just run some exes. There's some Azure exes executable that simulates the cloud on the local machine. And one cool thing about this, then you can see through your, oh, that's not the one. Fabric. Oh, let me just do it right here. Okay, so here, part of the Azure SDK is that it provides you can see what's happening in the local fabric simulation. So you can go to, okay, this is my one instance of indexer. I can see all those debugs spewed for the events that are happening, so I can track what's happening in here. And then, as soon as I run it, the local, as you can see, the 127 address, this is the web role that's running on the local fabric as well. And this is the Silverlight APIs. You can drag and drop all these controls in there, which is kind of cool, I thought. And then, and you can easily come in here and say, oh, now I want 2 instances, right? And then I run it again. And here, well, has it shut down? No. Okay. Now there's 2 instances of indexer here, and then totally 4 instances of the rows. Okay, one web row and 2 worker rows, and it's very easy for them to debug and see what's going on. And when it's all done, when it's all done, they just have to go in and say, I want to publish it. As soon as I click publish, and it's going to create, all the files going to be packaged together and push it online. So that's basically it. And in conclusion, there's great potential for cloud application in the health science, medical imaging area. For number one, for healthcare providers, right, that don't have a big IT staff, we can easily provide some sort of solution, storage solution in the cloud. And for third world countries, where they can't even, keep the computer secure in a hospital, let alone a data center, right? They can use the cloud environment to store all their data in other premises instead of that's more stable. And NIH just funded an $18 million project for all the craniofacial researchers, just to collect all those craniofacial data, CT scans and pictures, into some sort of a hub. And then so people can use all those data to do research and analysis. And these type of collaboration, cloud solution is really ideal. Right? People can just push their data into a central hub and then share their data for analysis. Diagnosis, treatment planning, clearinghouse. The insurance company would be able to use this to lower the cost of healthcare. And Microsoft Health Vault, right? They run in the cloud, and they also implemented the support for DICOM images. Up till I think recently, you can't even upload DICOM images to Health Vault, but you can do it now recently, and they run in the cloud. So there's plenty of potential application for that. And incorporating cloud computing in the curriculum, there's multiple ways to do it, and we found the Capstone project to be one of the efficient way. And great Azure, and the students all love it. They found it to be a great learning platform and with really awesome tools. With that, I think we have a couple minutes for questions.
First of all, let's thank you.
Yes?
I assume that your some of the various instances that are running, that those are also like straight console write outputs that you
Oh, in the fabric?
Right.
Here. Yes, these are just console outputs. Right? You can't do anything with it. I mean, it's just they're showing.
This is because you're running locally.
That's correct. That's correct.
If you're actually running on the cloud, you can't see that anymore.
That's correct. Each of them is in a VM. If you're running in a cloud, each of these instances is in a VM. So the only thing you have is the logging, right? They provide some sort of logging mechanism. You can see what happens, but you can't really see what's going on. So that's why this is really handy. You write and debug your code locally. This is when you run in a local simulation, it's basically an Oleksii, a console app that implements the wrapper for all the APIs, to simulate a VM. But as a console app, you can see all those.
Will breakpointing and all that kind of stuff work?
Oh, yes. Here. Yes. Good question. Here, you can set all kinds of breakpoints in here, and then breakpoints will break, and you can step through the code. That's what's great about it. You can run this whole thing locally in a simulation, almost like for real. And you can set breakpoint and step through the code and so forth.
Does that logger that you mentioned, the one that is available in the cloud, is it available locally as well?
That I'm not sure. That I'm not sure. I would imagine so, but I can't say for sure.
One of the challenges of debugging, this is very good, by the way. I've done my share of these Azure applications, and you did a very good job of describing it. One of the interesting challenges in the debugging side of things is you might put something in an application that might just say, I'll throw an exception, and I'll deal with that problem. That'll tell me when I have an error. and then you catch it in the local mode. Actually, even in the emulator, it will still do this. But once you push it to the cloud, if it throws an exception, the cloud is designed to be completely resilient. So it sees an exception, and it says, "Oh, I'll restart it for you." And so,
Yes.
so you try to figure out, well, how come my application? I know something must have gone wrong because I threw an exception there, but it's still running. And you can't kill it because the cloud is designed to prevent errors. So you have to get used to it. That's where the logger comes in. You learn the
Yes,
logger.
and even with that, it's like printf of old, right? It's still a challenge, to debug. Not Microsoft Azure alone. All the cloud platform, has the same problem. But this is great.
Any other questions?
No?
Okay.
All right.
Thanks again.
Thank you very much.
So the next we have Oleksii Morozov from the University Hospital of Basel, and he's going to talk about rapid diagnosis of heart disease by cloud-based high-performance computing for computer vision.
I cannot. No, it's my computer. So, welcome everybody. I would like to present an approach to rapid diagnosis of acute heart disease by cloud-based high-performance computing for computer vision. So first of all, I would like to remind you about the importance of the heart in our life. It's a life-sustaining pump with enormous activity, which pumps about 2.5 million liters of vital blood to all our organs. This enormous activity is due to special structure and functioning of the heart. And as any other organ supplied by the blood, the heart requires its own blood supply system for oxygen and nutrition delivery. And this system is called coronary artery system or cardiovascular system. And a failure of such system, of this system, is the most frequent cause of heart malfunction and death. According to statistics provided by World Health Organization, heart diseases, in particular coronary artery diseases, is the world's largest killer, taking more than 17 million of humans' lives every year. Cardiology is a field of medicine which is aimed to prevent, diagnose, and treat heart diseases. Not a long time ago, cardiologists were using a limited number of tools for diagnosis, for assessing the function of the heart. Currently, they have more tools, more information, but unfortunately, analysis of this information still remains quite subjective and depends on the experience of a particular doctor. How do we see the cardiology of tomorrow? So we believe that there will be even more advanced technologies used for assessing the function of the heart. They will provide multidimensional, multimodal, high quality, high resolution, maybe providing possibility to analyze the heart on the cellular level. So the doctors will have possibility to get quantitative, objective, and integrative analysis result from the data they acquire, and there will be worldwide networked standards, reference data sets available for learning and for studying the diseases. So what are the problems to achieve, to get such features? So first we need an enormous computing power, so available in a distributed environment, but only for a fraction of time. So few seconds is necessary for the doctor to get the analysis results and to try to get a solution, especially in acute cases. So, and there is need in global storage network for storing large data sets and accessing them. Some notes about cardiac ultrasound, which is one of the modern tools for evaluating the heart function. It's based on transmitting and receiving high-frequency sound waves into the body. It doesn't use any radiation ionization, does not introduce ionization. It's totally safe, non-invasive, very fast, portable, and relatively cheap. One minus is that the quality of the signal is rather low, but there are ways to further improve the signal-to-noise ratio. About the diagnostic value of ultrasound imaging, so first we can assess how the walls of the heart function and possibly identify event of myocardial infarction, which basically is the death of heart muscles. We can assess the pumping function of the heart by segmenting three-dimensional images. We can assess the function of the valve. Here is in particular an example of so-called valve regurgitation, which is just simply malfunction of the valve, so it doesn't it passes the blood through when it should be closed. What makes cardiac ultrasound really powerful is the possibility to get three-dimensional information about the heart. So first steps were based on very simple technology of freehand ultrasound, where the doctor was moving the transducers manually, and after the data were reconstructed in 3D. Still used and providing high quality 3D information, mechanical sweeping of ultrasound transducer, and the most recent technology flies 3D based on 2D arrays of ultrasound transducers with electrical sweeping. What is cardiac ultrasound machine today? Is a combination of a transducer, which gives the data, and basically essentially a supercomputer, which processes the information in real time and in offline, providing analysis results. And it's relatively cheap. It's much cheaper than an MRI machine, but still quite expensive. And what is very interesting is that it's in idle 90% of time, in particular in Switzerland, in Swiss hospitals. What computational problems do we solve? We solve in cardiac ultrasound. First of all, we have to reconstruct the signal which comes from the transducer. So we have to basically we have non-uniformly sampled data which we need to reconstruct to complete gridded or continuous representation. In 2D, it's done in real time, and it doesn't create any problem. But in 3D, there are some problems. There are different sources of non-uniformity of the data, including inherent non-uniformity of scanning process, non-uniformity in synchronization, which is ECG signal, and body motion artifacts, for example, breathing, which introduces some non-uniformity in time and in space. And in total, we have four-dimensional non-uniformity, so with quite complex structure, and we have to reconstruct the full four-dimensional representation of the data. There are some mathematical techniques to do that. One of them is B-spline-based reconstruction proposed by our collaborators from EPFL Lausanne. It is the way of robust global interpolation, which helps to solve problems of oversampling, undersampling in different areas of the physical space. It is sparse, well-conditioned, and enjoys multi-resolution properties, which leads to fast solving algorithms. And it's parallelizable, and was successfully applied to 2D problems. But there are some problems in application of this technology, spline technology, to 3D and 4D. So complexity, the memory and the computational requirements, they exponentially increase depending on the size of the data, the grid size of the data. And in particular for this insufficient for analysis size, we have to deal with 78 billions of non-zeros, which is more than 300 gigabytes of data in single precision. Recently, we proposed a tensor-based approach which helps to overcome this problem, which dramatically reduces the storage requirements and led to feasibility to compute such problem on my dual-core laptop in 30 minutes. Yeah, this is an example of reconstruction, 3D, 4D reconstruction from a continuously rotating dataset, ultrasound dataset. Another type of problems, more complex problems in ultrasound imaging is tissue and blood motion estimation. And state-of-the-art technology to get this information is Doppler measurements, which are semi-quantitative by their nature. And to solve this problem, there is an extension of B-spline methods proposed by Unzer and Aragovindan, which is, can be applied to reconstruct the full motion information from grayscale images and Doppler data. And in addition, we can employ some additional physical constraints on the solution of the data based on fluid dynamics. This is an example of reconstruction of 2D plus time data from the tissue, from the so-called, in ultrasound imaging, it's called speckle tracking, from only grayscale images, but it can be combined with Doppler for better robustness and provide continuous and fully quantifiable information for the doctors. This is an example of blood flow and reconstruction from Doppler data, where the Doppler data combined and produce continuous and fully quantifiable information using B-spline technology. So what are the pathways for distributed computing and solving our problems? Well-known multi-core, cluster, GPU array, FPGA accelerator cards. Actually, we are currently exploring this pathway within ICS Microsoft sponsored project for building a real-time FPGA-based ultrasound machine. And one of them is cloud, in particular Microsoft Azure. So what are the reasons of using a cloud and building a cloud-based ultrasound processing service? First of all, processing of large multidimensional multimodal medical data requires vast computational power. And building and maintaining own infrastructure, computational and storage infrastructure in hospitals is overly expensive. And it's quite rarely used. This HPC power is quite rarely used, only a few times per day by a single doctor. It should be available at multiple points of care, medical practices, hospital emergency rooms, and it needs unified storage access to the multimodal medical data. This is a block diagram of a possible cloud processing service, where from the user side, so the user acquires 4D information and has some desktop built-in or mobile phone or laptop built-in abilities to visualize, to have some simple visualization of the data the user requires. The data is sent to the cloud for processing and storage, and as soon as the cloud computed all the information needed for the doctor, it can be accessed using an interactive web-based interface for visualization of signal and analysis results. Records data represent raw data stored in DICOM format for unified storage and access. And in addition, there can be an option to send data by parts for possibility to pipeline the process of analysis to provide the user coarser resolution preview quality reconstructions and analysis results. The process of solving in our algorithms is based on iterative improvement of solution, where we use linear operators. Here's an example of how the solution improves over the number of iterations. The distribution of the computations performed by the operator can be simply done by distributing subparts of the output among the compute units. But the problem is that while the output subparts are completely independent, there is some dependency in the input. And at each iteration, this data is transferred among adjacent units, and this is basically the factor limiting the maximal performance of such processing. And here are some estimations of the impact of this factor to the performance. So you can see that with 1,000 units for this data size, 32 gigabytes in single precision, and using InfiniBand recent communication technology, the algorithms can be the speed is about 1,000 iterations per second, which is rather good. This is excluding the CPU time. But it turned out that in this case, the most limiting factor is the computational load. For the same size and for more than 100 million of data samples, the total requirements, computational requirements for a single, in total is of about 5 teraflops with 3 terabytes of memory transfers. And you see how the performance is increased. So the inter-unit communication time does not matter in this case. And we need more than 1,000 compute units to run the algorithm at the speed of about 4 iterations per second. Hopefully, using multi-resolution, we can solve this problem by using coarse-to-scale propagation. And we can use multi-grid solving algorithm, which is based on the iterative improvement of the solution from scale to scale. In total, it requires much less computational load and few iterations at each scale to get reasonable solution. With the count of using multi-resolution, the total requirements per compute unit were computed. So, and what we have and what is acceptable for our purposes is about 1,000, more than 1,000 compute units to really get a rapid result, which is very important for acute cases. Motion reconstruction algorithms require approximately 9 times more computational load. We also estimated costs of such a ultrasound processing service, and what we got is in particular for Switzerland with uniform load is about 3,000 instances, yes, running during 1 hour, which is about large instances, so which is about $3,000 US, which is not that cheap, to be honest. The cloud it does not only enable the computations performed in cardiac ultrasound, but it also enables collaborative research and makes It provides a globally available service for processing and storing and accessing medical data using standardized DICOM interface. It can involve all interested parties around the world, which is very important to collect really worldwide, to make worldwide trials. And it is possible to get more statistics for rare case using worldwide trials, and it is possible to build reference data sets for known cases. So we presented an approach to rapid diagnosis of heart diseases using cloud-based distributed computing. Basically, we propose to replace ultrasound machine supercomputer by a cloud service for remote processing and storage, which, in our opinion, can lead to miniaturization and decrease of the cost of medical equipment, availability of advanced analysis technologies for objective analysis for any cardiologist or a doctor. In general, it can lead to availability of this technology to latest technologies at multiple points of care, unified storage and access of medical data, and enables collaborative research. And we believe that at some point in the future, in nearest future, there will be mobile ultrasound devices or medical devices in general, like this USB-based ultrasound, 2D ultrasound machine, which will work on multimodal, multidimensional data and will use cloud computing service to get full information about full 3D, 4-dimensional information. Yeah, thank you very much for your attention.
So the assessment of data transfer is based on InfiniBand?
I just took, yes, the most recent technology. I don't know what is inside of the Windows Azure architecture.
Remote access, I believe that you would have to go across the wide area network in order for the data to go.
I assume that I have only local communication between the compute units. So I don't assume that some of the compute units reside in Asia, other ones reside in Europe. So yes, I assume that they in the same compute center, yes, data center. But
I wish I could tell you that the network inside the data center was InfiniBand.
InfiniBand, yes.
I wish I could tell you that.
Okay.
Unfortunately, I cannot tell you that because I would be lying.
Okay, so, but as I explained, so the most limiting factor in our case at the moment is really the need in performance for a single compute unit, yes, or number of compute units. So, but the problem here, the solving algorithms, they scale very good. So, and yes.
So I guess maybe I'm missing something, but I thought the raw data you acquired from the ultrasound sensor has to go up to the cloud.
Yes.
Is that a large amount of data?
Okay, sorry, I misunderstood you. Yeah. So the amount of data sent to the cloud is not that large. It's not 32 gigabytes. It's maximum about 100 megabytes, but in addition, we can use compression, some lossless compression to to decrease the amount of data. And as I explained, in addition, we can use some pipelining, so to send parts of the data to really to get some preview.
DICOM does not really want you to compress anything.
Excuse me?
So I thought the DICOM standard does not really allow you to compress it.
No. You can. DICOM.
It's lossless compression.
DICOM.
That's correct, but it's very highly compressible. It's mostly black.
Yeah. So approximately half of the image, each image acquired in cone beam acquisition or fan beam acquisition scheme. So is black pixels. Yeah, because of the nature of acquisition. So it uses fan beam acquisition. Yes, and DICOM interface is extremely flexible, too much flexible. So it makes even problems for research because many producers of ultrasound machines, they introduce their own private tags in this interface. And for us, it's extremely difficult to get raw data for some producers like Philips, for example, Toshiba, and so on. So GE is a little better, yes, so we can get some raw data from raw images, not raw data, yeah. Not compressed, not JPEG images from the, yes. So this is, yeah, but this problem, yeah.
You said that you got the processing time for regular processing with the tensor-based
yeah.
down to 30 minutes, you said, on your dual-core system. So what sort of speed are you expecting to get on the cloud for that same calculation?
Yeah, I showed that approximately in 4 seconds.
4 seconds.
In 4 seconds using multi-resolution iteration, so we can get solution, in particular for signal reconstruction problem. In 40 for a grid size, for data grid size, 512 for each dimension in space, and 64 for time dimension, which is quite good resolution, yes.
Well, I don't misunderstand what you said, that because you said in order to get it faster on your desktop, you switch from the B-spline to tensor. But you said you're doing B-spline.
No. Mathematically, this solving algorithm is based in general on use of B-splines, on the use of B-splines. But the way how it is computed, so originally it was computed just using standard common way using matrices, sparse matrices. So, and we identified some structure which helped us to resolve this problem of memory, very huge memory, high memory requirements, and to solve problem on of quite big sizes on laptop. Yeah.
I see. You're changing how you.
Yeah, but the speed, of course, so on multi-core is not enough to get really rapid result, which is the requirement for acute cases. Yes. That's why we need larger power. Yeah.
So, did you think about the fact that a lot of the servers on systems like Azure or Amazon, you can actually require an instance which is a multi-core instance. Mm-hmm. So you have more than one core per compute computation. That can really have a huge impact on performance.
I counted this because I presented estimation of the time for quad-core for quad-core CPU, even with larger clock rate, with bigger clock rate, 2.7 giga. I know that in Windows Azure the instances come with 1.6 gigahertz clock rate, yes, and 4 cores for large instances, so I.
Actually, you can get up to 8 cores for large instances.
8 cores. So with 8 cores, I expect. Twice, yes. Not twice, because there is memory transfer, killing factor, yes.
You say that's 8 cores for a single worker.
Yes.
Yeah.
You pay 8 times as much.
Yeah, about $1 per hour, so.
The other thing is the data center in Europe is 3 times faster than the data center here. The Azure centers.
Okay.
It's newer.
One in Dublin?
Yeah.
One in Dublin and the one in Amsterdam.
I know that current quad, so the maximum number of instances is 20. How is it possible to get 1,000? Yeah. And is it possible currently?
Actually, right now, I think, you can, well, it depends upon the size of your bank account. Future business that you would have.
Okay.
But seriously, let me. We've done applications with 200 cores, and that's not too much. How far have you gone?
I know the models, I think we've gone up to 300 or so.
Several hundred. I don't. The problem that you find with something like Azure, as well as Amazon and others, is that the VM deployment, for the deployment time, beyond a certain number of instances starts to really get you. And so they try to, the Azure folks basically say, try not to go more than 200 instances of a worker role. because the fabric controller itself starts to get sluggish at that point.
Okay.
And you start seeing timeouts. But I think that's a temporary thing.
Yeah.
That's a temporary thing. Okay, I want to thank you once more. And also, this is very good. It's a small but highly engaged audience, so that's nice. And so everybody knows about the reception and dinner now, and how to get there? Okay, yeah, you just sort of walk. If it's not, let's see, we have sunshine, we have rain, we have hail, and I don't know what it's doing now, but it's an easy walk to get over there.